Chapter 11, Kinetic Theory of Gases, Section 11.2, Three-dimensional speed distribution of gas particles. In the previous section, we have derived the normalized probability density function of velocities in the x direction, which is this. F is the probability density function. Vx with an arrow on top is the velocity in the x direction. The square root of m over 2 pi kbt, this is the normalization factor. And over here we have e to the power of negative mvx squared over 2 kbt. This is the kinetic energy in the x direction over kbt. The reason I didn't put an arrow here is just because Vx squared is equal to Vx with an arrow squared. Now let's look at the y direction. We have the same equation, except x is replaced with y. And now we have the same equation for z. All three dimensions, they have the same normalized probability density function. Now, because the motions in the three dimensions are independent of each other, that means how fast a particle is moving in the x direction and how fast it's moving in the y direction do not depend on each other. The normalized three-dimensional velocity distribution function is simply the product of the lowercase f of Vx, f of Vy, f of Vz. So we just need to multiply the three. For example, if you threw 3 dice, the probability of getting, for example, 1, 1, and 1 is 1 over 6 for the first dice, 1 over 6 for the second, 1 over 6 for the third. So you can multiply them together, you get 1 over 216. Alright, that's why we do multiplication here. The probability of 3 events happening at the same time is equal to the product of the probability of event 1 happening at that time multiplied by the probability of event 2 happening at that time multiplied by the probability of event 3 happening at that time. That's the meaning of this. Alright, now we just multiply the three probability density functions in the x, y, and z direction. We can see this normalization factor is the same in these three equations. So now we have this m over 2 pi kbt to the power of 3 halves. And then we have a Gaussian function of Vx, a Gaussian function of Vy, and a Gaussian function of Vz. We can combine this. Over here we have Vx squared plus Vy squared plus Vz squared. What is this? Well, this is simply V squared, and V is the three-dimensional speed. So actually this probability density function of the velocity in the x, y, and z direction can be rewritten as this simpler function. Again, it's m over 2 pi kbt to the power of 1.5, and then e to the power of negative the three-dimensional kinetic energy over kbt. The SI unit of this function is a little weird. It's second divided by meter and then to the power of 3. The normalized three-dimensional velocity distribution function can be written as this. We have a normalization function in the front. We have a Gaussian function of the three-dimensional speed over here. And we know this has to be 1 if we integrate the velocities in the three dimensions from negative infinity to positive infinity. And we call this dvx, dvy, dvz as the volume element of this triple integral. So really this dvx will be integrated from negative infinity to positive infinity. So will this dvy and dvz. And then we can convert this integral with this volume element in the simple xy coordinates to a more complex spherical polar coordinates. The spherical polar coordinates of 3D speed depends on three things. One, the magnitude of the three-dimensional speed. And two, the angle between the velocity vector and the z-axis. And three, there's another variable. So if you project the three-dimensional vector to a xy plane, then you get a two-dimensional vector. And between the two-dimensional vector and the axis, we have the third variable. We call that phi. Alright, so the volume element of the spherical polar coordinates of 3D speed is this. It's v squared sine theta dv d theta d phi. We will prove this in the next slide. Now let's look at this. We have this equation. Alright, this is equivalent to this equation. It's just we changed the orthogonal vx, vy, vz coordinates to a spherical v, theta, phi coordinates. V is from 0 to infinity because v is now the three-dimensional speed. Theta is the angle between the velocity vector and the z-axis. And theta is from 0 to pi. Finally, phi is the angle between the x-axis and how the velocity vector being projected onto the xy plane. Now we have this integral equivalent to this integral, so the value should be 1, and we can plug in the expression of this uppercase f over here. Okay, this is a Gaussian function of the three-dimensional speed, so really this should be 100%. And theta and phi are corresponding to the latitude and longitude of a sphere. It's just when we are talking about Earth, the latitude is usually from north 90 degrees to south 90 degrees, a span of 180 degrees in total. We have also a span of 180 degrees in total, or pi. Longitude, if we're talking about the geography, I think it's usually from west 180 to east 180, with a range of 360 degrees. And over here we have a range of 360 degrees, which is just 2 pi. The speed ranges from 0 to infinity. Over here it's just because we want to integrate all possible speed. Now we're going to answer this question: why is the volume element v squared sine theta dv d theta d phi with this kind of limits? We'll have to look at two graphs. I'm going to use xyz for a simpler explanation. In a Cartesian coordinates, the volume element of space is dx, dy, dz. If you try to integrate over the entire space, we just need to integrate dx from negative infinity to positive infinity. dy also, we have y from negative infinity to positive infinity. And so does this dz. In the spherical polar coordinates, however, we're going to have to do things a little differently. So this box-like shape is the volume element in the polar spherical coordinates. So we're going to approximately get the volume of this, alright, by assuming this is indeed a box with 3 side lengths. This side length is dr. So first you have r, and then you extend it by an infinitesimal amount, which is just dr. Alright, this is dr. And also we're going to just draw an arc. This is theta, so from here to here it's theta. Theta is the angle between this vector and the z-axis. We're going to extend it by an infinitesimal amount from theta to theta plus d theta. And then this arc is simply r times d theta. So now we have dr and then also r d theta. This one is a little bit tricky because it contains three components. You do have r sine theta and d phi. So if we project this three-dimensional vector onto the xy plane, the length over here is r sine theta. This is r sine theta. And then we have an angle phi here. And we can extend this phi just a little bit to phi plus d phi. And then, we can rotate this a little bit more, which is d phi. D phi times this radius give you this third side length. This radius is r times sine theta, and then multiplied by the angle d phi. We got the third one. Now we just multiply dr, r d theta, r sine theta d phi all together. You get r squared sine theta dr d theta d phi. So this is why we have this kind of volume element for the three-dimensional speed. Okay, and over here we can just simply replace r with v. We get this volume element for speed. Now the integral of the normalized probability density function must be 1. So we have this is 1. Alright, and we can separate the variables. We see three different variables: v, the three-dimensional speed; theta, the angle between the velocity vector and the z-axis; and phi, well, you have to project the velocity onto the xy plane and then find its angle with x. So you have v is from 0 to infinity, theta is from 0 to 2 pi, phi is from 0 to 2 pi. Alright, so we have this. Now let's separate the three variables. We have three single variable integrals. Over here, an integral of v, an integral of theta, an integral of phi. The integral of phi is simply just 2 pi. The integral of sine theta is negative cosine theta from 0 to pi, and the result is 2. So this is 2, this is 2 pi, together you have 4 pi. And also, if you compare this equation with the previously learned probability density function in the coordinates of vx, vy, vz, we have one additional term, which is v squared over here, v squared. Alright, now we have the probability density of gas particles moving at a three-dimensional speed within this range, v to v plus dv. It's this. Note that this v is the three-dimensional speed. Alright, and dv is the differential of the three-dimensional speed. And then we have this equation. So it's not simply the uppercase F anymore in the Vx, Vy, Vz coordinates. We do have additional terms. We have V squared here, we have 2 here, we have 2 pi here, and together it's 4 pi V squared. The uppercase F again is just this, alright? It's just the distribution in the x direction multiplied by y direction multiplied by z direction. So that's why we have this n to the power 1.5 and e to the power negative mv squared over 2 kpt, and this v squared is vx squared plus vy squared plus vz squared. So we just have one additional term, 4 pi v squared here, when we are examining the probability distribution of the three-dimensional speed between v and v plus dv. So it's going to be this. Well, again, if you have a gas particle, the probability of finding the particle moving at a speed from here to here is simply its probability density multiplied by the range you're given. The range is dv, so really it's just this times dv. Alright, now what if we need to find the most probable three-dimensional speed? We'll have to just maximize this equation. How do we maximize the equation? Well, at the maximum, the slope should be 0. So we're going to just take the differential of this equation. It looks a little complicated, but it's doable. This part is constant. It does not depend on v. 4 pi does not depend on v. So we're going to just evaluate this. I'm going to use the product rule. V squared goes to 2v. That's the first derivative. And over here I need to get the derivative of this Gaussian function of v. So I'll copy v squared here, right? And now I'm gonna view this whole thing as a variable. I set a variable, maybe alpha to be this. So e to the power of alpha, I just copy that e to the power of alpha here. And now I need to take the derivative of alpha with respect to v. It's this. Alright, it's just variable substitution and also the chain rule in calculus. How do we solve this equation? First, the Gaussian function and Gaussian function. Well, we can make them disappear. Just both sides of the equation divided by the Gaussian function, right? And then we have 2v and then minus mv cubed. V squared times v cubed over kBt. Solve this, we get the most probable three-dimensional speed. Alright, it's the square root of 2 kBt over m, or square root of 2RT over uppercase M. M is the molar mass in kilogram per mole. Let's look at helium as an example. The square root of 2RT over m, 2 times R times temperature over the molar mass of helium in kilogram per mole. We get 1100 meter per second. It's really fast. Well, the probability density distribution function, or simply probability density function of the three-dimensional speed v is this. Again, don't forget about this 4 pi v squared term. If you don't remember this, actually this is simply the surface area of a sphere that has a radius of v. That's just 4 pi v squared. So really, if we multiply this 4 pi v squared by dv, you're gonna get a volume of a shell. The shell has a thickness of dv. The spherical shell has a radius of v. And then you can probably better understand this 4 pi v squared. Now we have this. Given this, we can also compute the average speed and the root mean squared speed. The average speed is actually the probability weighted average. Alright, so this is average. By the way, the average can be denoted by a pair of bracket, a bar on top, or AVE in the subscript. Either way, so these three are just notations for the average speed. To do that, so we have this speed, right? We have speed over here, and then over here, from here to here, that's the probability of finding a particle moving at a speed between v and v plus dv. So we have this. So this is v times the corresponding probability, and we integrate everything. That's the physical meaning. The problem is this: how do we integrate this? It looks very complicated. We always simplify the Gaussian function first. What I'm going to do is I'm going to simply set q to be mv squared over 2 kBt. So I'm setting this whole thing to be q. So you get e to the power of negative q. Alright? And then because of this, v squared is just 2 kBt times q over m. And then v is simply the square root of this. Now we can simplify everything. So first, we write out the average speed over here in terms of v, and then I will start to replace this whole thing with q. V squared is just this guy. dv squared is just the differential of this guy. So now we have this equation. We can of course take 2 kBt over m out. We take this out as well, so you see this twice. I copied 2 pi here. I copied this m over 2 pi kBt to the power of 3/2 here. Alright, and then we have a very simple integral right here. It's a very simple integral. It's just e to the power of negative q times q. You can do this by hand if you're good at calculus. Mostly you just need to move this into this d and then use the product rule. Alright, but now I'm gonna just give you the expression of this integral. It's this. Plug in 0 and infinity, the result is 1. So this integral is just 1. And then we combine all other terms. Alright, all other terms. You do have kBt on the bottom, and it's kBt to the power of negative 1.5. Also you have kBt and another kBt, so it's going to be kBt to the power of 1/2. You have mass to the power of 1.5, but over mass squared, so you have this mass on the bottom inside the square root. You do have a pi here, and you have pi to the power of negative 1.5, so you have pi on the bottom. You have a 2 here, you have a 2 here, you have a 2 here, that's 8. But also you have this one. This one is actually 1 over the square root of 8, so you have the square root of 8 over there. Yeah, from here to here, it is tedious, but it's very simple algebra. If you are patient enough, you can go from here to here. And this integral is simply 1. You do need to know how to do the evaluate this. The probability density function of the three-dimensional speed is this. Again, it's this. Now let's look at the probability weighted average of v squared. Well, sometimes we'll just say, well, this is just a root mean squared. Why? Because we square this v first, and we take the average, and then we take the square root. Alright, so it's right here actually. Root mean squared. We have the speed squared first, that's why I squared here. And this bar means average or mean. And then a square root over here, that's root. So that's why this is called a squared root mean squared, or RMS speed. Now let's look at this. The probability density function is given over here. Now let's look at the average of v squared. It's just this. We put v squared here, and this is the probability of finding the particle moving at a speed between v and v plus dv. So this whole thing is the probability. Okay, without dv, that's probability density. With dv, that's the probability. Alright, the probability weighted v squared, you integrate this. And again, we just set variables to make things easier. What I'm going to do is I'm going to set this whole thing to be q squared. Okay, this whole thing to be q squared. So q is just the v times the square root of m over 2 kBt. And of course, correspondingly, v is q times the square root of 2 kBt over m. So you use this equation to get this equation. Now we have this integral written. From here to here, a bunch of algebraic operations. I think I copied 4 pi to here. I copied this to here. Where does this come from? This comes from, I think it's just because v is q times this thing. So you have this thing squared, and over here you have that thing again, and over here you have this thing that's squared. So squared to the power of 1, so overall to the power of 5. So we need this to the power of 5. That's this. And now the integral is simply e to the power of negative q squared times q of q to the power of 4. This is not trivial. I didn't want to do this by hand. It's doable, but I used the Wolfram Alpha. So if you just download this PowerPoint file. You can click this. You can see how Wolfram Alpha tackled the problem. The value is 3/8 times the square root of pi for this integral. If you really want to do it by hand, it's doable. It's just we will keep lowering this power, until the power becomes 0, and then we know the integral of e to the power of negative q squared dq from 0 to infinity is square root of pi over 2. That can be proven, but it's really tedious to tackle this integral, so I'm gonna just use the value from Wolfram Alpha to put it in here. I combine everything here, it's this, and then in the end we got this. Finally, the root mean squared three-dimensional speed is the square root of this guy. It's the square root of 3 kBt over the mass. And just because v squared is the sum of vx squared, vy squared, and vz squared, and also the distribution in the x, y, and z directions should be the same. So when you see this, you should just give 1 kBt over m to vx squared, 1 kBt over m to vy squared, and 1 kBt over m to vz squared, and then you have 3 of them. Alright, so if you're looking at the root mean squared one-dimensional speed, well, it's just square root of kBt over m. You can prove this as well, given the distribution in the x direction. You can prove this as well, but I'm not gonna do that. This is to summarize the 3 different quantities. We have the root mean squared three-dimensional speed, we have the average three-dimensional speed, we have the most probable three-dimensional speed. They share something common. They all have the square root of kBt over m, kBt over m, kBt over m. They do differ by the number in the front. You have 3 here, you have 8 over pi here, you have 2 here. The square root of 3 is 1.732, the square root of 8 over pi is 1.596, the average is 1.414, and you can see this is larger than this is larger than this. Now let's look at a numerical example. Let's look at the RMS, root mean squared, average, and most probable speeds for the nitrogen gas at room temperature. It's more convenient to pre-calculate the square root of kBt over m, so I did that here, and then multiplied by the square root of 3, we get the RMS speed. Multiplied by the square root of 8 over pi, we get the average speed, and also multiplied by the square root of 2, we get the most probable speed. And you can see the order of the 3. 515, 475, 421. Alright, so there's 3 numbers. You can just do a simple calculation yourself. Let's say there are only 3 particles moving, and their 3-dimensional speeds are, for example, 1 meter per second, 2 meter per second, and then let's say 6 meter per second. 1, 2, and 6. And then somehow you can just compute the root mean squared and the average. You'll see this is always greater than this. Alright. For the most probable speed, well, you need more data point. Again, let's look at the 3 equations. Most probable, average, root mean squared. They share something in common, which is the square root of kBt over m. Square root of kBt over m. They differ by a coefficient. Square root of 2, square root of 8 over pi, and square root of 3. They are just 1.414, 1.596, 1.732. Alright. And now let's look at some distributions of the speed at different temperatures. Low temperature 100 K, high temperature 1200 K, really high temperature 3000 K. This is the distribution of the speed at different temperatures. You can see at lower temperature 100K, this distribution is narrower. All right, and the average is this is average, this is most probable, this is RMS. Those are in the lower end. Now if you increase the temperature, we have most probable, average, and RMS speed. Okay, higher numbers. Finally, 3000 Kelvin. Again, the same order, most probable, average, and RMS. Much larger numbers over here. Just to summarize, at low temperatures, the distribution is narrower. At higher temperatures, the distribution is wider, and also toward the high speed range. You can see, some molecules move at 3000 meter per second over here. Over here, at most for this 100 Kelvin, roughly 1000 something. Over here, more than 3000. We also need to look at another factor, which is the mass. We did see temperature on top, so if you have a higher temperature, you have a larger RMS, average, and most probable speeds. But what if you have a larger mass? M appears on the bottom, so larger mass means slower particles. You're gonna get smaller numbers. Now let's look at the distribution of three speeds. For helium, neon, argon, and xenon, you have the mass numbers 420, 40, 132. You can see over here, this is xenon, argon, neon, helium. Helium has a wider distribution because it can span into the really high speed region. So over here you can still see a decent probability density over here, and look, it's in the unit of second over meter. So again, second over meter. Alright, so over here, this is just because the unit of this is the unit of probability divided by the unit of the range of the speed. The unit of the range of the speed is meter per second. The unit of probability is it's unitless, so that's why you have this. Right, for helium, it's possible to have a decent probability with like 2500 meter per second. Neon, so about here. Okay, the high-speed neon molecules, high-speed argon molecules, and atoms, high-speed xenon atoms. And also, it's really easy to find the most probable speed. So that means just the maximum probability density. So we find out here, here, and here, and here for xenon, argon, neon, and helium. So if you take the ratio between those probability density, it's going to be the square root of 1 over 132 versus the square root of 1 over 40 versus the square root of 1 over 20 versus the square root of 1 over 4. You see, this is proportional to the square root of 1 over the mass. So we can make quick predictions. If you compare just neon and helium, neon weighs 5 times that of helium. Therefore, you can see helium is the square root of 5 times of the speed of neon. And you can also compare argon and helium. They differ by 10. Therefore, those speeds differ by the square root of 10, with the lighter gas particles traveling faster in general.